Hello everyone. This is the first lecture of week 10. So, in this lecture we will try to complete our discussion on simplex method. Please recall that in the 9th week we discussed simplex method in detail. We started with the reasoning why vertices are the only possibilities of solutions in an LP problem, we discussed simplex method step by step, starting with the basic feasible solution and verifying whether a given point is the minimizer or given vertex is the minimizer or not, and then exchange of a variable from the sets of basic variables and non-basic variables, right. So, and we finally did the coding as well. Okay. So, in this lecture we will first go through the code once more. Okay. So, if you look at the algorithm that we discussed, we first write down these variables b, n, cb, cn, b set, n set and little b, right, and we print x is b inverse b comma 0, right, and so after that we verify this particular condition. So, when this is not true, that is the sum is equal to 0, then vertex that we have found is indeed the minimizer, otherwise it is not. So, then we move ahead to exchanging one variable from between the basic and non-basic variable sets, right. So, this is to welcome the incoming basic variable from non-basic variable set, and this part is to throw out a particular basic variable in the non-basic variable set, right. So, this performs the exchange, and this is again the printing, right. So, I would like to suggest one change. In some of the places this might actually cause an error. Okay. So, for exchanging the values in two variables, right. So, that is you want to take the value of b to a and from a to b. Okay. So, there is a nice way of coding in Python, which is a comma b equal to b comma a, right. So, that performs the exchange very nicely, right. But for example, if you are working in, let us say C, C++, languages of that sort, such a change is not possible, because you will actually have to create a temporary variable, right. So, because in the same line you cannot do the exchange, right. So, if you write a equal to b, then both a and b have the same value, then you cannot then write b equal to a. So, you will have to create a temporary variable and then do the exchange. Okay. So, in Python, if you are just exchanging two scalars, it is not a problem, you can do a comma b equal to b comma a. But if you are actually exchanging two vectors, sometimes it might cause a problem. Okay. So, this is just exchange of two scalars, not a problem. This again is exchange of two scalars, not a problem, but here it is an exchange of two vectors, right. So, that might actually cause a problem. So, I would like to change that. Okay. So, I first introduce a temporary variable, okay, put it as a copy, and now put the qth column of n, the jth column of b, and the qth column of n will be equated to t. Okay. So, I will remove this line. This is because when you exchange two vectors, a comma b equal to b comma a may not work well in Python. So, of course, with that change you can still run the code again, will not have any problem. I missed a comma here, I am sorry, otherwise you get the same answer, right. Okay, fine. So, we have worked out this particular example, right. So, this was the example we worked out, right, where maximized the value of x2 subject to the condition that the feasible set is a triangle with vertices 0, 0, 1, 0 and half, half. Okay. So, yeah, I will work out maybe one or two more examples, and then I mean also discuss some drawbacks of this algorithm in this lecture, okay, and in the next lecture onwards we will go to a different method. Okay. So, yeah, let us actually consider this particular LP to be precise, 3x1 minus 2x2 plus x3 subject to the conditions that x1 minus 2x3 greater than or equal to 4, 2x1 minus x2 plus x3 greater than or equal to 2, and yeah, x1, x2, x3 greater than or equal to 0. Okay. So, yeah, it is a 3-dimensional LP. So, yeah, drawing and finding out the vertices is a little hard, okay, and we are not going to try that because at least in 3 that you can make an attempt, but if you have 4 variables, yeah, then forget it, 4 or more variables, then forget it, right. So, let us not do that here either, right. We will just try to follow the algorithmic approach without taking on the geometry, right. So, yeah, let us first, this is actually of the form Ax greater than or equal to b, x greater than or equal to 0, right. Let us first convert this of the standard form, that is the first step, right. Here, yeah, the first step is to convert the LP into standard form, right. So, let us do that. So, I will rewrite this as the first constraint as so x1 minus 2x3 greater than or equal to 4 becomes minus x1 plus 0x2 plus 2x3 plus x4 less than or equal to minus 4. Okay. So, if you write this as minus x1 plus 2x3 sorry equal to minus 4 and x4 greater than or equal to 0. Okay. So, if you just write this as minus x1 plus 2x3 less than or equal to minus 4, you can add x4 and yeah, add this greater than or equal to 0 as well. So, the next one is 2x1 minus x2 plus x3 greater than or equal to 2. So, this becomes minus 2x1 plus x2 minus x3 plus x5. Okay. So, since it is a new variable, I will write it slightly away, and this is minus 2, this is x5 greater than or equal to 0. Okay. So, yeah, now we have the A matrix. So, yeah, the A matrix is actually minus 1 0 2 1 0 minus 2 1 minus 1 0 1. Okay. Yeah, and this is x1 x2 x3 x4 x5 that will be x, and B is minus 4 minus 2. Okay. Yeah, now we have the following problem. It is min 3x1 minus 2x2 plus x3 subject to Ax equal to b, x greater than or equal to 0. So, yeah, I can even write this as plus 0 x4 plus 0 x5. Okay. All right. So, now we have the standard form ready. So, the next one is to find the basic feasible solution. So, for that you will have to figure out two linearly independent columns, right. So, yeah, you can see that except for columns 2 and 5, right, the columns 2 and 5 are exactly the same, but otherwise every pair of columns are linearly independent, right. So, you can choose any of them. Let us check one of them. So, for example, we can try x4 and x5. Okay. So, yeah, suppose xb equals x4 x5. Okay. So, then yeah, xb is actually equal to b inverse b. So, b is just 1001, that is I, and which is then it is just b, which is minus 4 minus 2. Okay. So, this is not greater than or equal to 0, right. So, this is not a feasible vertex, not a feasible vertex. Okay. So, since b is actually negative, it would be good to take a negative column, right. So, let us actually take the first column, which is both negative, right. So, let us actually take x1 and x4. Okay. So, of course, these two are linearly independent, minus 1, minus 2 and 1 0, right. So, yeah, now let us actually find what is x b, right. So, yeah, that is b inverse b. So, yeah, so yeah, it is x1 comma x4. So, here you have minus 2 and 0 and minus 2, right. So, it is clear that x1 should be 1, right, and when you put 1 here you get minus 1 and minus 3. Okay. So, yeah, that is actually a problem, because here again you can see that this is not greater than or equal to 0, right. So, that is not true, again not a feasible vector. Fine. So, we will now select x1 and x5. Okay. So, then you will have yeah, xb, which is x1 comma x5. So, here you have minus 1 and 0. So, x1 is 4, right. So, 4 into minus 1 is minus 4, and 0 into whatever is 0. So, that is minus 4. Now, you have minus 8 and 6. Okay. So, yeah, you have so this is certainly a feasible vector. Right. So, therefore, yeah, our basic feasible solution is x1 is 4, x2, x3, x4 are 0, and x5 is 6. Okay. So, fine, we will start with this as the basic feasible solution. Okay. So, yeah, we have actually converted the given LP into standard form. We have got a basic feasible solution. Okay. Now, yeah, we can do all of this. Of course, we can work it out by hand, but if that is what we were going to do, we would not have written the code, right. So, let us actually figure out what is b n, c b c n and all that, and then plug it into the code, right. So, that we get the answer immediately. Okay. All right. X b I have written as x1 x5, right. So, we have b equals minus 1 0 minus 2 1, okay, and n is 0 2 1 1 minus 1 0, okay, the other 3 columns basically, and C b is 3 and 0, C b transpose, and C n transpose is minus 2 1 0, okay, and B is minus 4 minus 2. And yeah, so since we are also asking for B set n set, yeah, B set will be 0 and 4, and n set will be 1 to 3. Okay. So, we will just copy down this in the code and find out the answer. So, B was okay, it is a 2 dimensional array, minus 1 0 minus 2 1, okay, and n is 0 to 1 1 minus 1 0, 0 to 1 1 minus 1 0, C b is 3 comma 0, C n is minus 2 1 0, this is minus 4 minus 2, and B set is 0 4, and n set is 1 to 3. Okay. So, with this we will try to work out the answer. Yeah, this is this was one other change I wanted to do, but forgot that. Okay. So, yeah, you can see that the answer is unbounded. So, some of the compilers allow this exit command. Okay. So, Google Colab somehow does not allow this. So, we will instead do break. Okay. Exit actually exits from the algorithm itself, break only breaks from the loop, but yeah, in at least in this case both are the same. So, when you break, yeah, you are breaking from the loop, and yeah, you are, I mean that is the end of the code as well. So, this is one other change that I want to do. Okay. If you do break, then that means it breaks from the loop, but if you do exit, yeah, it exits from the code itself. Okay. But yeah, this is only allowed in some of the compilers. Google Colab does not allow this. Nevertheless, fine. So, yeah, this was the answer expected. So, it says that the problem is unbounded. So, it first started with 40006, which is what we did. B set was 04, N set is 1 2 3. Then there was a change of 4 and 1, because of which you got 46000, and at that point, yeah, the code found that the problem is unbounded. Okay. Yeah, so yeah, look at this problem in the topmost line, minimize 3x1 minus 2x2 plus x3 subject to this condition. At least it does not appear straightforward that it is actually an unbounded problem, right. So, yeah, I will theoretically argue or rather mathematically argue why it is unbounded now. Okay. So, previous lecture we saw a toy example where you maximize x1 plus x2 such that x1 plus x2 greater than or equal to 1. Of course, if it is greater than or equal to 1, it can go even up to infinity, right. So, that is why it was unbounded. So, let us see what is the problem here, right. Okay. So, note that these are the constraints. You have x1 minus 2x3 greater than or equal to 4 and 2x1 minus x2 plus x3 greater than or equal to 2, right. So, suppose I fix if x1 minus 2x3 equal to 4, then x3 is x1 by 2 minus 2. Okay. So, let us take it that way. Now, similarly, if 2x1 minus x2 plus x3 equal to 2 and x3 equal to x1 by 2 minus 2, then you have x2 equals 2x1 minus x3 minus 2, right. So, I just brought x2 here or rather x2 here and 2 here, yeah, there will be a plus, I am sorry, yeah, but x3 is x1 by 2 minus 2, right. So, this will become 5x1 by 2 minus 4. Okay. So, note that this is actually a feasible point, yeah, if x1 is large enough, right. In fact, if x1 is yeah, so if you put 2 here, no, if you put 4 here, this is equal to 0, and yeah, so if you put 8 by 5, I think, so 8 by 5 into 5 by 2 is 4, yeah, so yeah, this will become 0 as well, right. So, for any x1 greater than or equal to 4, right, x1 by 2 minus 2 and 5x1 by 2 minus 4 is feasible. Okay. So, in fact, yeah, it satisfies these conditions with equality, okay, these two conditions, and yeah. So, if x1 is greater than or equal to 4, you can see that all three are greater than or equal to 0 as well, right. So, yeah, so this is actually feasible. Okay. So, now let us find out what is the value of the objective function. So, it is 3x1 minus x2 plus sorry 2x2 plus x3, right. So, at this feasible point, right. So, you will have 3x1 minus 5x1, that is minus 2x1 plus x1 by 2 is minus 3x1 by 2. Okay. So, now you have 8 minus 2, which is 6. Okay. So, if you keep increasing the value of x1, okay, so if you put x1 is equal to 100, right. So, for any x1, note that this point x1 by 2 minus 2, 5x1 by 2 minus 4 is feasible, right. So, I can keep increasing x1 indefinitely, and you can see that the objective function keeps decreasing indefinitely, right. So, yeah, when you drive x1 to infinity, you will see that the objective function is driven down to minus infinity. So, yeah, that is the reason. So, yeah, I will write that down. Yeah, if x1 tends to infinity, yeah, then x1 by 2 minus 2, 5x1 by 2 minus 4 remains feasible, but objective function goes down to minus infinity. Okay. So, yeah, that is the reason, yeah, the problem is unbounded. Okay. So, yeah, this was one example I wanted to work out to give you a feeling of why the unboundedness is necessary, right. Yeah, otherwise you might still be thinking, do we ever get a problem where yeah, we would actually get unbounded, right. So, yeah, I wanted to give you an example. Okay. I think we have worked out two examples, which is okay. So, before closing our discussion on simplex method, right, I wanted to discuss about two issues in the simplex method, right. So, one of the issues is something that we saw in this problem itself, right. So, if you check yeah, this particular problem, the first step of course is converting the given feasible set into standard form, right. So, given LP into its standard form to be very precise, right. The second step is finding out a basic feasible solution, right. So, that is not just finding m linearly independent columns, right. So, here, yeah, it just involved finding two linearly independent columns, but just to converge to a basic feasible solution I had to work quite a bit, right. So, because, yeah, in each of the cases I was seeing I mean at least one of the components of the basic variables being negative, right. So, imagine you have a 100 dimensional problem, okay, and you have to choose 50 linearly independent vectors, right. So, yeah, you try choosing a possible 50 linearly independent columns, and imagine you end up with B inverse B less than or equal to 0. Sorry, I mean one of the components of B inverse B less than 0. Okay. So, all of what you did is a waste. Go back, start with another 50 linearly independent columns, check if B inverse B is greater than or equal to 0, if not, go back, right. So, the process of finding a basic feasible solution could actually be mind boggling, for example. Okay, yeah, if you get it in a few attempts, it is great, but what you have to do to find a basic feasible solution is just trial and error, like, yeah, whatever we are trying, right. So, yeah, that is actually a problem. Yeah, I mean we can work out the simplex method only when you start with a basic feasible solution. So, yeah, that could be a hard task in case I mean there are not many feasible vectors. Okay. So, that is one of the problems. Okay. Okay. So, the first issue is finding a BFS initially could be a hard task. Okay. Fine. So, there is one more issue which is possibly more exciting to know. Okay. So, recall that we were saying about moving around vertices, right. So, yes, so let us say you start with a BFS. Okay. One way of finding the answer, I mean without going through the simplex method, is find all the vertices and compute the objective function for at all the vertices, choose the vertex that gives you the minimum, right. So, we rejected that, saying that yeah, in big problems, let us say yeah, higher dimensional problems to be precise, right. So, in higher dimensional problems we could end up with issues like yeah, searching for too many vertices, right, and we went to the simplex method. What is the guarantee that the simplex method will not traverse all the vertices, right. So, we have given a method yeah, which has some nice heuristics, which is good, but do we have a guarantee that whatever problem I give, whatever pathological example that I give, okay, the number of vertices that the simplex method traverses will be very small, okay, is there a guarantee? Unfortunately, the answer is no, okay. We actually have a pathological example, okay, which I am going to give you now, okay. If you have n variables, okay, it traverses 2 power n vectors sorry 2 power n vertices before coming back to the original solution, okay. So, yeah, that could be surprising given that I mean simplex method was supposed to give the answer in a very few steps, right. I mean that is the reason why we did the switching of vertices, right, by exchange of basic and non-basic variables, right. But yeah, I am going to give you the following example, okay. So, the issue is this: the worst case in simplex method ends up traversing 2 power n vertices, okay. So, yeah, what is the problem? The problem is as follows: you are going to maximize 2 power n minus 1 x 1 plus 2 power n minus 2 x 2 plus dot 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 2 x n minus 1 plus x n, okay. So, yeah, this is the objective function that you are going to maximize subject to n constraints. What are they? So, the first constraint is x 1 less than or equal to 5, the second is 4 x 1 plus x 2 less than or equal to 25, the third is 8 x 1 plus 4 x 2 plus x 3 less than or equal to 125 dot dot dot. You have yeah, so the last one x n will be 1, but for x 1 you will have okay. So, for 2 you have 4, 3 you have 8, yeah, so it will be 2 power n, 2 power n x 1 plus 2 power n minus 1 x 2 plus dot 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 plus 4 x n minus 1 plus x n less than or equal to 5 power n, okay, and of course x non negative, okay. So, you have n plus 1 constraints. The first one is x 1 less than or equal to 5, next one is 4 x 1 plus x 2 less than or equal to 25, then it is 8, 4 and 1, 8 x 1, 4 x 2, x 3, the sum of that less than or equal to 125 and so on until 2 power n x 1 plus 2 power n minus 1 x 2 plus dot 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 4 x 1 minus 1 plus x n less than or equal to 5 power n, okay. So, yeah, it is a proper LP, right, and yeah, so if we do all the work that is required, right. So, you will have n constraints, right. So, you will have n slack variables. So, you have 2 n variables, right. A will be quite large, okay. So, the first one will be 1 0 0 0 and this will also be 1 0 0 0, the second one is 4 1 0 0 0, this will be 0 1 0 0 0 and so on until 2 power n minus 1 dot 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 4 and 1, this will be 0 0 0 and 1, okay. So, this is A, yeah, x can be x 1 to x 2 n, right, and yeah, B is 5, 25 dot 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 5 power n. Okay. So, you have got A, you have got B. So, I am going to choose this as capital B, right. So, yeah, of course, B inverse B is non negative, that is very clear, because it is 5, 25 dot 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 5 power n, that is greater than or equal to 0, and x1 to xn is 0, right. So, that is where we are starting at. Okay. So, this is B, this is n. Okay. So, I have got B, I have got n, I have got little b, and CB is zeros, okay, n zeros, Cn is minus 2 power n minus 1, minus 2 power n minus 2 dot 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 minus 2 minus 1. Okay. Yeah, and of course, you will have B set, n set is already clear. So, it is 0 to n minus 1 is n set, n to 2n minus 1 is B set, right. So, alright, that is what you will have as capital, maybe I will just write that down. B set is n plus 1 to 2n minus 1, and n set is 0 to 1. Okay. Alright, so this is basically what is the variables whatever we need. Okay. So, let us write that down. Okay. So, yeah, we will first write maybe n is equal to 4, and B is identity of 4, and okay, capital N is okay. So, okay, we will hard code it for 4. Okay. So, that is 1 0 0 0 and 4 1 0 0 and 8 4 1 0 and 16 8 4 1. Okay. And CB is just zeros of 4, but Cn is yeah, we have minus 8, minus 4, minus 2, minus 1, and B was, if you recall, it is 5, 25, 125 and 625, and B set is 4, 5, 6, 7, and this is 0, 1, 2, 3. Okay. So, let us check. You can see that it takes 16 iterations, right. So, we started with 0. So, yeah, the right answer is 0 0 0 625. Yeah, these are auxiliary variables, right. So, but it has taken 16 iterations, right. So, I can try to do that with n equal to 5, okay. With very minimal changes I can do it. So, let me do that. So, I have to include zeros. Okay. So, here it is 5, and here you will have minus 16, and here you will have 3 1 2 5, and here, yeah. So, this should go away, and you will have 8 comma 9. What happened? And this will be 4, and yeah, n does not matter. Now, you can see that it takes 32 iterations to give the right answer 0 0 0 0 3 1 2 5. Okay. So, yeah, and you can check for higher values of n as well. I mean, you can this can be a small exercise that you can try, where you actually write it for general value of n. Okay. So, yeah, you have to modify these to satisfy general values of n. Okay. So, when you do that, you will see always that you will have, the algorithm actually takes 2 power n iterations, right. So, yeah, because of these two issues, we will actually go for some other algorithm, okay, which we will start in the next lecture. Thank you.